Hi everyone, good afternoon. And today we'll learn about ILD influence line diagram of indeterminate beam. So if you have already studied about ILD of determinate structure in structure first, so it become quite easy. There is nothing uh, difficult, or there is nothing different apart from few things. There is nothing different between the ILD of determinate structure and indeterminate structure. So let's begin. I have written one question and I'll just solve this question of ILD. At the same time, I'll be telling you the concept that we need while solving ILD problem of indeterminate structure. So the question is, draw the influence line diagram for the shear force at the point C having length of 5 meter and give the ordinate value at 1 meter interval. So first let me draw the question. I guess the question is this is point C, this is B, and this is 2. So I guess this is the question. So the question is asking us to find the shear force, to draw the ILD for the shear force at the point C. At the point C, what we have the shear force, we have to draw the ILD for that shear force. So if you want to go directly to calculate the shear force at C, it becomes quite difficult. So what we do is, first we find this shear force. First we find the influence line diagram due to the reaction at A, and due to reaction at B, and then it becomes easy for us to calculate the ILD for the shear force at any point throughout the beam. And if you don't know, this is a prop cantilever beam, because one end is fixed and other end is roller or hinge, so it becomes the prop cantilever beam. And this question I'll be solving by using Muller-Barsalou principle. It is one of the easiest concept to solve the indeterminate structure. So what does this Muller-Barsalou principle says is, if you want to draw the ILD, first we have to make the indeterminate structure as into determinate structure, and the degree of external indeterminacy of this types of question is always 1. Not always, but most of the time it is 1. In this case also you can easily see this is 4 minus 3. There are 4 reactions, and we have 3 equation of equilibrium. So that is why you can easily solve this. I'll rub this. So we'll remove one support, and we'll place VB over there, reaction at V. This is reaction at A, and here somewhere the point C, this is 3 meter and this is 2 meter. Here maybe here is bending moment, but for shear force we don't need bending moment. But you can, but you will need bending moment, this MA, when you have to find the influence line diagram for the bending moment at point C. That is time you need MA. What in this question you don't need. And one more thing, that is, to solve this kind of beam or this kind of question, you should have the basic idea of conjugate beam, because Miller-Barsalou principle says that if you want to find the ordinate of ILD, influence line diagram, of any point, like I am calculating the ordinate of influence line diagram due to reaction at B, that VB, that becomes del x b by del x del bb, that is deflection at any point. Suppose at point C, that then it becomes C due to load at B, due to the reaction at B, reaction force at B, divided by deflection at B due to reaction at B, or due to load at B, or due to force at B. So and it become easy for us to find the deflection on the conjugate beam method, because in conjugate beam, if you divide the bending moment at any point by EI value, you will get the deflection at that point. So we will draw the conjugate beam of this real beam. So conjugate beam is nothing, is the imaginary beam. You have to place unit load here. You can place it upward as well. It does not matter, or it does not make any sense. The only thing is you'll get the answer positive, or you'll get the answer negative if you just interchange the load pattern. And why have written 1 here? Because we are going to find the conjugate beam. So for that, we have to place unit load at here and remove all the load. So for conjugate beam, we will get a maximum bending moment over point A, because this is fixed support, that is 1 into 5. This will become 5 by EI. Similarly, this will become 4 by EI. Similarly, this will become 3 by EI. This will become 2 by EI. This will become 1 by EI. In this way, we find the ordinate at 1 meter interval, because in question it asking us to find the ordinate at 1 meter interval. That is why we have found out deflection in bending moment diagram at the interval of 1 meter. Now by using this, okay, so now by using this conjugate beam, we'll find the deflection at every point, 0, 1, 2, 3, 4, and 5, and we'll find the ordinate of ILD due to reaction at B. So we'll draw this first. So this del 0, you won't have any deflection at point O, because point O is a fixed support, and fixed support you don't get any deflection. So that's why d0 becomes 0. Similarly, d1 is deflection at point 1, and that how you calculate? You calculate the deflection at point 1 using the area of multiplying the area of this trapezium into its centroid. But to find the area of centroid to find the area of trapezium may be easy, but the centroid of trapezium become quite difficult. That is why we divide this trapezium into two triangles. This will become triangle 1, this will become triangle 2. Now we'll calculate the area of this triangle, multiply by its CG, calculate the area of this triangle, upper triangle, and multiply by the CG. So that is 1 by 2. I'll consider this as a base. That will become 5, and this will become height. What is the height? This 1 into center of gravity 2 by 3 into 1. Since we are here, from here, this triangle, this is from this point, this point, if you go toward this point, then you will get the CJ 2 by 3 of this total base. In upward 1 by 2 into base, I'll consider this 1 into height, I'll consider this 4 into this 1/3 only. From here, from this point, you will get CG at 1/3 of 1. You will get something. D2 will get similarly. This is again 4.2. We consider this trapezium, and again we will divide this. This is one triangle. This is second triangle. This triangle again I will consider the base as 5 and height as from here to here. This is 2. 2 by 3 into 2. A proper triangle 1 by 2. Base is 2, height is 3. This is 1/3 of this is 2. See, you can take height and breadth as anything, because since it is multiplication, you get the same answer. So it does not matter to you all, or don't get it wrong. So in this way, you calculate deflection at point C, deflection at point 4, and deflection at point D. So I have already calculated, so I'll just write the value. D1, you will get D1 as D1 you will get 2 point. If you calculate, you get 3.2.332. Similarly, for D2 you get 8.66. 8.66. If you calculate D3, you will get it as 18. If you calculate D4, you will get it as 29.332, 29.332, and D5 you will get as 41.66, I guess. 41.66. These are deflection that you will get at 1 meter interval throughout the span. So now coming to the ordinate of ILD for shear force, or for the force due to the reaction at BV or B, that is BV. So ordinate BV you will find it by using Mueller and Basalo principle, and it states that deflection at X due to B is divided by deflection at B due to B. And see, this D5 is also deflection at B, because in this beam this is D5, right? This is D5. D5 what? Deflection at point D due to load at point B only, right? So that is DBB, deflection at point B due to load at B. Here it was like deflection at point 4 due to load at B. You see, deflection at point X, any point X, it is load at B divided by deflection at point B due to load at B. So this we have as 41.66. So now we'll find the ordinate of every point. So this is like distance, this is X, this is BB ordinates. So when X is 0 divided by, because when X is 0, this point X becomes 0, because when X is 0, del 0 is 0, divided by 41.60 becomes 0. When X is 1, you get, when it is 1, you get 2.332 divided by 41.66. This is 2, you get 88.66 divided by 41.66. For 3, you get, what was 3? 18, I guess. 3 is 18. 18 divided by 41.66. Similarly, 4 is 29.332 divided by 41.66. And the 5 is, what is 5? 5 is 41.60 divided by 41.66. Then we get 1. Right. Uh, so you get 0.0559, this you get 0.207, 0.432, and this you get 0.704, 0.04. So I think these are the value that we get. I might be wrong, so I request you all to calculate it using your own calculator, because I have done so quickly. So these are the ordinate, and if you draw ILD of this if you draw the ILD due to point or due to the force at B, you can just point at 0. This is 1, this is something something, and here is something, here something, but don't draw a straight line like this. This is wrong. It should be like this, or it should be like this, because this is basic difference between the ILD of determinate structure and indeterminate structure. Indeterminate structure, if you remember, you have drawn or used to draw the line as a straight line, but in indeterminate structure you have to draw with curve. So it may be the curve like this, or it may be the curve like this. Now we will uh, solve our question. Now it is time to solve the question. It was just ordinate due to the force at B, that is reaction BB. Now you can calculate B also, BA also. That is simple. That is 1 minus BB, because when in this beam, this is BB. When unit load is at point C 1, what will be the value of BA? That will be 1 minus BB. So 1 minus, what will be 0 at X equal 0. When X is 1, this become 1 minus 0 point, I don't know what was 0.0559, you get something. When X is equal to, it become 1 minus 0.204 or something. So you can calculate the value of BA in this way. Now coming to the point. Now for the shear force at point C, to solve which we have to divide a span into two portions, that is AC and BC. So if you have studied in sector first or in zone about shear force, then how does shear force act in a beam? It acts in this way: half portion upward, and just the left portion downward, or the left portion upward and the right portion downward. And if you join this, they get cancel each other. So this is how the shear force looks like if you separate the beam, or if you just divide the beam into two sections. Now when the unit load is in AC, when the unit load is in AC, now you can consider the portion AC as well, or you can consider portion BC as well. So when unit load is in AC, why would I consider AC? It becomes difficult for us. That's why we consider BC, and then BC become VB, because there's no load, there's no external load, so BC become VB. And now what are the ordinate of VB? When VB is, let me drink water. When unit load is at X is equal to 0, BC becomes 0. When unit load is at X, because we're considering this portion, because unit load is in this portion. So when unit load comes at 1, what get BC? What will the value of VB at 1? That is 0.559, I guess. When X is equal to 10, BC becomes 0.704. 204. I guess I might be wrong. When x is equal to 3, the BC become, what is the value of BB at x is equal to 3? That is 0.432, I guess. So this is how we calculate the ordinate of ILD for the force shear force when the load is between A and C. Now when the unit load is in the portion is in BC, when it is in BC, what is the value of BC? This is 1 minus B. When the unit load is at in the portion BB, BC become 1 minus BB. Now we can consider this portion as well, but it may be difficult because we have to calculate the value of BA first, but we have only the value of BB, that way you consider this portion. So 1 minus BB. What about the value of BB when unit load is at portion x is equal to 3? Now unit load is at exactly at point C, that is 3. Value of BB was 0.432, and you get something. If we calculate, what we get? 1 minus 0.432, and we get 0.568. When x is equal to 4, BC become 1 minus, what is the value of BB when it is when the value of BB when x is equal to 4, it means, I don't know. I hope you have calculated all the value of BB at when x is equal to 1, x is equal to 2, x is equal to 3, x is equal to 4, and x is equal to 5. Similarly, when x is equal to 5, you get BC again something. This you get 1, that is 0, because exactly at 5, that is point B, the ordinate will be 0. So this is how we calculate the ordinate. This is how we calculate the ordinate of the ILD for the shear force at point C. Now when you are drawing, again draw it, or don't draw it as a straight line, because this is indeterminate structure. In I don't you get this 0.432, and you get 0.56 or something. 0.05, you get 0.20 something. You have got similarly. This is at 4 point. This is 4. This is 3. This is 2, 1, 0, and this is 5. So this is a figure of ILD, the force, shear force at the point C. In this way, we calculate the influence line diagram. We draw the influence line diagram. We calculate the ordinate of it. So if you have any questions regarding the ILD or regarding this question, you can freely ask it in the comment section. Just thank you for today.